Hello and welcome to Chapter 5. Today we're going to look at Section 5.2, Quantum Theory and the Atom. If you recall from Chapter 4, we talked a lot about the discovery of the protons, neutrons, and electrons, and we were kind of starting to talk a little bit about the behavior. In the early 1900s, we had a Danish physicist named Niels Bohr who was actually working in the same lab as Rutherford was. What he did is he was kind of interested in how things were bonding and how the electrons and all that kind of stuff worked. So Niels Bohr is kind of famous, or one of the things he's known for is proposing a model for a hydrogen atom. So what he did is he proposed that the hydrogen atom has only certain allowable energy state. So within this, he has the lowest energy state, which is what we call the ground state, okay? Then as an atom gains more energy, okay, and this can come in many different forms, but as it gains more energy, it's going to go into what we call an excited state. So as it goes into an excited state, then it's going to move out into a different level. And I'll have a picture of this here in a second, and we'll talk more about this. But ultimately, what Niels Bohr did is he related the atom's energy states to the electrons within the atom. So he suggested that the electron in a hydrogen atom moves around the nucleus in certain circular orbits, and the smaller the orbit, the lower the energy state. Therefore, as we start adding energy, that orbit is going to get bigger and bigger. So to give you a visual, this is kind of what he was talking about. The red dot here is the nucleus, okay, and hydrogen in the ground state configuration has one electron that's going to orbit it. So Niels Bohr proposed that as energy was added to the system, that electron was going to jump out and go farther and farther away from that nucleus depending on how much energy and which energy state it was in. So to kind of complete his thought on this, what Bohr did is he assigned a number n, which we call the quantum number, to each orbit for his calculation purposes. So the first orbit that was the closest to the nucleus, he said was n equals 1. Okay, and this would be the ground state level for a hydrogen atom, is when that electron was in that n equals 1 orbit, and that's because it doesn't radiate any energy. Now, as outside energy is added, and that capital E is going to represent energy, okay, so as outside energy is added, then the electron is going to move into a higher orbit and then goes into what we call that excited state. Now, as with many early theories, okay, Bohr's model did a great job of explaining a hydrogen atom. However, it did kind of lack too. Okay, so when we're talking about these orbitals, one thing you need to know is that the orbitals are not evenly spaced apart, and we'll kind of talk about this more later on. But the things that Bohr's model did do well is, like I said, it did explain hydrogen very well, but it failed to explain how other elements worked, okay? And it didn't fully explain the chemical behavior of atoms. So although he was on the right track, he still had to have his theories and ideas revised. So in the mid-1920s, roughly, we have a French grad student named Louis de Broglie, okay? And what he did is he proposed kind of like a fix to Bohr's model. And what he did is he actually went and he compared the electron orbits of atoms to waves. Okay, so whether you think of like a sound wave or like a wave in the water, okay, we have wavelengths and wave behaviors, and that's kind of what de Broglie noticed, and he applied that science to the electron orbits, and he was much more successful. I do have a video link here, and this will be posted on the Maurer Math site, so you can watch that. It actually does a really good job at talking about the mechanical wave model, or what we know as the quantum mechanical model now, okay? And the quantum mechanical model is nothing more than the fact that it's a model where the electrons now are going to be treated as waves instead of circular orbits. Okay, it's also sometimes known as the mechanical model, and although it's similar to Bohr's model in the fact that it limits the electrons or the energy, okay, that's what the capital E is, remember, it limits electrons' energy to certain values. The only difference is that it does not try to describe the electron path, because with an electron, Bohr said that things go in a circular model constantly, and if things are going more in a wave-like pattern, then it's a little bit harder to predict. And even still today, the electrons' movement around the nucleus is not fully understood. So the boundary of an atomic orbital is still unclear, and it, as far as we know, it does not have an exact shape. Now, when we're looking at what we call the hydrogen atomic orbitals, we have what we call principal quantum numbers. Now, these are similar to what Bohr came up with when he was assigning the quantum numbers, where the n equals 1, n equals 2, and so on. When we're looking at principal quantum numbers, okay, and these come from de Broglie's model, the quantum mechanical model is going to assign 4 quantum numbers to atomic orbitals. And that first quantum number is what we call the principal quantum number, or is represented with a lowercase n. So what the principal quantum number does is this indicates the relative size and the energy level of atomic orbitals. As n increases, the orbital is going to grow, and the electrons are going to spend more time away from that nucleus, which means that it's increasing in energy. Now, each major energy level is what we call a principal energy level. And with principal energy levels, the lowest energy level is assigned a principal quantum number of 1. Okay, and we can go up to 7 energy levels. Remember, the capital E's represent energy. So for hydrogen, we have up to 7 energy levels for hydrogen alone. Okay, and then within these, we have energy sublevels. So principal energy level 1 will have 1 sublevel. Principal energy level 2 will have 2 sublevels. Principal energy level 3 will have 3 sublevels, and so on. Now our sublevels are going to be labeled with either an S, a P, a D, or an F. And that's all going to come from the shape of the atom's orbital. Now this is something we'll talk about, I'll have you look at, but you're not going to be required to memorize shapes at this point in time. Okay, we are going to talk quite a bit about S, P, D, and F, okay, throughout this chapter, but you do not have to know or memorize the actual shapes. But for a point of discussion, S orbitals are going to be spherically shaped, like this. A P orbital is going to be shaped kind of like a dumbbell. And the D and the F orbitals are a little bit more complicated, okay, and they're not all the same. But right here you can see we have the example of a D orbital, and this right here, the F orbital, is a lot more complex. Okay, and with our orbitals, okay, each orbital will contain at most 2 electrons. Okay, now this is something that you are definitely going to want to remember. Okay, so each orbital will only hold up to 2 electrons. The single sublevel in principal energy level 1 corresponds with the 1s orbital. And the S sublevels only have 1 orbital. We have 2 sublevels in principal energy level 2, and those will be the 2s and the 2p. Keep in mind that 2s is going to be larger than a 1s, and the p sublevels are going to have 3 orbitals. Now, I'm going to stop right here for a quick second. Some of this might be kind of confusing, but I think as we go over our notes in the next couple of days, this stuff is going to make a lot more sense. So today I'm just going to ask that you write this stuff down, kind of think about it a little bit, but we are going to talk about this way, way more in depth, and I'm going to show you some easy ways to remember this over the course of the next couple of days. All right, so to continue on, our P sublevels, okay, because in our second sublevel, principal energy level, we have 2 S and 2P, so 2S is larger than 1S, but our P sublevels, we're going to have 3 orbitals. So our S's only have 1, Our P's are going to have 3. Then when we jump up to principal energy level 3, we have 3 sublevels. We have the S, the P, and the D. Okay, so D's now have 5 orbitals of energy, while P's had 3 and S's only had 1. And then once we get to that 4th sublevel, we have S, D, P, and F. Okay, and our F sublevels are going to be the largest, and this has 7 orbitals. So if you notice, these kind of go up incrementally, okay, and they are odd. So our S, this has 1, our P has 3, our D has 5 orbitals, and our F is going to have 7 orbitals. Now, if you recall from the top, okay, each orbital, we said, contains 2 electrons. So ultimately, the S orbital will hold 2 electrons. The P orbitals can hold up to 6. D's can hold up to 10. And F's can hold up to 14. So I'm just going to ask you to keep that thought in the back of your mind as we go through things over the course of the next couple of days. Okay, and just to give you a picture, okay, and again, you are going to, by the end of this chapter, you'll know how to draw these and you can come up with these on your own, but I'm just going to try to show you a picture to maybe give you a little bit of an idea as to how this works. So for this element right here, this right here is the 1s level. And notice each of these arrows are going to actually represent an electron. So we have 2 electrons in the 1s. Then the 2s is going to be a little bit higher up, or it's a little bit higher energy level than the 1s. Okay, and again, it's an s orbital and it only holds 2 electrons. Okay, then if I go up to the p, remember we said that the p has 3 orbitals. So here's 1, 2, 3 orbitals, and each orbital can hold up to 2 electrons. So I have 2 electrons here, and then I have 1 electron here and 1 here. And we'll talk about why there's 1 in these 2 and 2 in this one. We'll get to that here in the next couple of days as well. But just so you can see, 1s is lower in energy than a 2s. A 2s is lower than a 2p. Okay, just like a p energy level or p orbital is going to be lower than like a d or an f. Okay, so this is going to conclude our notes for today. Please let me know if you have any questions. Otherwise, I will see you in class tomorrow. Thanks and have a great day.